Hello, welcome to my channel. Once again, my name is Uma, and I do request that if you are new to this channel, you first subscribe and like the videos, and then you can proceed. I do thank you for your support. So last time we looked at how to design a whole slab floor, a whole block floor, and we stopped at the design of the design selection of main reinforcements. And now today we want to look at the deflection check and the shear check for the same. So right, and now the check for deflection is provided for in Eurocode 2. That is section 7, Eurocode 2, section 7, whereby we shall base our calculations, and basically we shall use table 7.4 to start our deflection calculations. This is our Eurocode 2. I want to head to that table 7.4, where we can get the basic span to effective depth ratios for the various stress levels and the span types. Okay, 6.6, 7.1, 7.2, 7. So generally, this is the clause we shall be referring to when designing for when checking our deflection. 7.4. If you want to do it from first principles, you can use this formula 7.6, part A and part B. But for us, basically, we are going to use this table. Since we are dealing with a slab, we know that a slab is quite lightly stressed compared to beams. Beams are highly stressed. This is because the slab distributes loads to a larger area or a wider area compared to a beam. And the slab we're designing for was an end span of a continuous slab. Yes, you know, hollow block or slabs. We design them as one-way slabs, and we basically designed for an end span such that our base key span to effective depth ratio will be 26 with a factor 1.3. That will be our start point. So heading back to our calculations, so our starting span to effective depth ratio will be 26, and then we multiply it with that factor 1.3, and then there are some other additional factors that have to be put into consideration. Okay, so the best key span to effective depth ratio that we read from our table uh, is calculated on the assumption that the reinforcement ratio is 0.5, and then the concrete compressive strength is 30, and the yield stress of the steel is 500. Therefore, by that it is further multiplied by several other factors to that do account for the difference in those assumptions that were made while deriving these figures with respect to what we are designing for. One of the factors that we multiply with it puts into consideration the area of steel provided, whereby when you provide more steel, the stress reduces, and then the other thing that boosts the ability to resist deflections is the section. The fact that we designed for a T section at mid span, there's a factor we multiply the best key span to effective depth ratio with, and that factor, all these factors are in Eurocode too. That very section for checking for deflection. Okay, those factors let me try to look for those factors. They are around this. Okay, this statement that these expressions, all the values in the table, have been derived on the assumption that the steel stress and the appropriate design load at subhabitally limited at a crack section at mid-span of a beam or slab or the support of a cantilever is written, which corresponds roughly to FYK, the yield stress for the steel, to be 500 megapascals. So where other stress levels are used, the value is obtained using expression. The values obtained using expression should be multiplied by this. So conservatively, we we shall multiply our ratio with this, which is also given by 500 over this, which factor, and from national annex to this very report, this ratio should not exceed 1.5. Okay, so whereby it is 500 over FYK, and since our FYK used in this example is also 500, this will cancel out such that we remain with area of steel provided over area of steel required, and automatically, since we always provide more steel than required, the stress in the steel reduces, hence leading to a higher span to effective deflection ratio, or higher resistance to deflection. But this ratio should not exceed 1.5. Though I made a mistake and included the provision for the flanged section, but let's see. This 0.8 should not be a part. So but our ratio okay, so our ratio is now 157 divided by 128. Which is actually 1.1.23 1.23. Okay, so that factor we're going to multiply that factor with the base key ratio, and also the other factor is due to the fact that we designed for a T section at mid span, whereby it's a place where we check our deflection. Okay. And from our Eurocode, it says for flange sections where the ratio of the flange breadth to the rib breadth exceeds 3, the values should be multiplied by 0.8. Okay, so then the other factor, it accounts for the span. For beams other than with spans exceeding 7 meters, of course, the more the span, the more the deflection. So with this, when the span exceeds 7 meters, the ratio will be reduced by this factor, be multiplied by 7 out over the span. But in our case, our span was 5 meters, therefore this factor automatically becomes 1, or it's ignored. So back to our flange section factor. Our flange breadth is 0.4 or 400 millimeters. 400, and then our rib width is 125. 125. Which we get 3.2. So which means we shall have to reduce our basic span to effective depth ratio by a factor 0.8. Okay, so we shall have to multiply now K times 26 times this 157 over 28, which gave us 1.23. This is 1.3 then multiplied by 1.23, and then we multiply by 0.8. Okay. That gives us 33, which is 33.26 as our required ratio. So after that, we are going to compare this with what we provided. What was actually provided is the actual span over the actual effective depth, which our span was 5,000 or 5 meter over our effective depth, which was 160 mm, and we end up with 31.5. So which means since this ratio is less than this, it means its denominator is more than the denominator for this ratio, whereby our denominator is the effective depth that we provided here, which means the effective depth provided 160 is more than what is actually required. This makes our rib adequate, or our depth adequate, whereby our rib automatically passes the deflection check. Okay. that is it with deflection. Okay, so next time, in our next tutorial, we shall look at the shear. We shall look at the shear check. Okay, thank you for listening. Have a nice time.